So now we discuss the nature of light. Okay, we see now nature of light. So it is a very critical and very complex to know the nature of light, because many experiments, the different type of experiments done with light and their experiment results and the many properties of the light cannot be explained by taking any one nature. Means for scientists it is become very difficult and it is very complex and problematic to understand the nature of light. So thus far finally all scientists agreed that to follow a double nature, a dual nature for light. Now we see that. So the nature of light, so it is not possible to explain all properties, all experiments of light by taking only one nature. So that's why the nature of light is taken as dual nature. Dual nature means generally we know the double role. So dual nature is applied to the light. So what are the two natures? One is wave nature, second is particle nature. So particle nature means corpuscles or corpuscular theory you can say. Corpuscles means small particles are treated as corpuscles. Means the all properties of light can be explained by taking wave nature sometimes and by taking particle nature sometimes. For example, if you want to explain photoelectric effect property of light, reflection, refraction, etc. So these are the main properties of the light which can be explained only by taking particle nature to the light. Nothing but a stream of particles can be considered, then only we can able to understand this type of experimental properties. So for example, even to explain the black body radiations, the particle nature is necessary to apply light. And see some other properties of light. So here you see photoelectric effect, reflection, refraction and black body radiations and some other. This mainly can explain only by taking particle nature to the light. Generally this particle nature to the light was applied by Max Planck and also Einstein. To explain the black body radiations and about the other electromagnetic radiations, Max Planck and Einstein given their theories, which also tells that the light is consists of some particles, not only in the form of waves. Next, before this, in very earlier days, Newton given a theory which tells that light is consist of a stream of particles which are named as corpuscles, that were known as corpuscular theory. That was known as corpuscular theory given by Newton in very earlier days. That Newton particle theory was able to explain the reflection. The Newton corpuscular theory, nothing but the particle nature. We said that reflection, refraction type of properties can be explained with the help of a particle theory. And even Max Planck and Einstein also proposed the particle theory for the light. But there is some properties of light which cannot be explained with the help of particle nature. So for example, interference, and diffraction. Interference, diffraction, nothing but so actually this diffraction can be explained generally in double split, or it is also given as double slit. Okay, double slit experiment. In the double slit experiment, the diffraction of the light takes place, and there also interference of light takes place in the many derivations, in the many experiments. Mainly in the derivation of Bragg's equation and lambda is equal to 2d sine theta. So there is a presence of some interference takes place. Means that to explain interference and diffraction of properties, it is impossible to explain these two properties by taking particle nature. It is just possible only by applying interference of light, diffraction of the light. So diffraction of the light is a very basic experiment, that is a double slit experiment. Double slit experiment form ID, this is diffraction. So these two can be explained, nothing but we can understand these two properties only by applying wave nature to the light. So that's why finally we can conclude, or nothing but all scientists conclude, that the nature of light is dual nature. It consists of nothing but it is in wave nature and also in particle nature. Means sometimes it behaves as like particle nature, sometimes it behaves as wave nature. It depends on the experiments and the other conditions of experiments. Okay. Mainly now we discuss about the wave nature of that light. Just leave the particle nature. We have only that limitation only for particle nature, and afterwards in the other topics we can discuss the photoelectric effect only. But the mainly have a discussion about wave nature of light. Okay. Now we discuss the wave nature of light. Okay. See, wave nature of light, or it can be called electromagnetic radiation. Now we see why it is called like this. So the wave nature mainly proposed by Maxwell, and he also James Maxwell at first proposed. He given a detailed explanation in a wide range. James Maxwell given a wide range explanation for the interaction of a charged particle interaction between a charged particle or charged body and electric field, magnetic field. At first he was able to explain in a wide range, in a macroscopic level, the interaction between the charged particle, charged body and with the electric field and magnetic field changes. He observed that fastly moving charged particle, nothing but an accelerated particle. An accelerated particle can produce fastly moving high speed charged particle, or an accelerated charged particle can produce electric field and magnetic field in the path of that charged particle. The charged particle moves in the form of wave, and there is also formation of electric field, magnetic field around it. So Maxwell suggested that there is a formation of electric field and magnetic field when a fastly moving charged particle or highly accelerated charged particle is moving in the form of wave. Here the charged particles are moving in the form of wave. In the same way, there is a formation of electric field and magnetic field, both takes place, which are also moves in the form of waves. That's why these are called electromagnetic radiations. That's why these are called electromagnetic radiations, as there is a presence of electric field and magnetic field. So now the main important is the position, now the directions, angles of this electric field and magnetic field and the path of this particle we see now. So if you just take so it is the direction of the charged particles propagation, which is moves in the form of wave. Why it is moving in this direction? This is the path of light, are nothing but charged particle. There is a formation of electric particle. We said that. So like this, there is a formation of, means the vertical wave. Okay. Vertically, there is a formation of a electric field takes place, which is perpendicular and vertical to the path of the light propagation, particular path of the charged particle propagation. Next, if you take it is the path of light. There is also a formation of a magnetic field. So magnetic field forms like this. Okay, this is also in the form of wave. Again, it is also perpendicular to this path of light. So this is horizontal. So that's why we make it like this. So this is magnetic field. In some books it is also referred as H, magnetic field. Okay. Means here there is a formation of electric field, magnetic field, this is the path of the light. These three are perpendicular to each other. So for example, if you take these three fingers, okay, just take it is the path of light propagation, a path of light propagation. So this is horizontal to it. This is horizontal to it. This is a light path, path of light. This is the propagation of light, and this is the horizontal and perpendicular to this path, where this indicates the magnetic field. Next, so this is vertical to this direction, vertical, but it is also perpendicular. So if it is taken at the path of light or propagation of light direction, so this indicates this direction indicates electric field. Means here the electric field, this is magnetic field. These two are perpendicular to each other, and these two are again perpendicular to the path of light. Mean totally the magnetic field, electric field, the path of the light. The three are perpendicular to each other. Okay, clear? For example, the path of light, so this vertical direction we can compare like for example, if a rope, just ఒక తాడు తీసుకొని it is connected, it is fitted to a pillar, just loosely fitted to a pillar, and just by shaking that rope, so we will get some waves. So that waves are like this, means they are vertical, means in that type there is a formation of electric field. And for example, magnetic field, for example, take a movement of snake. Movement of snake is also like wave, but there is a totally parallel to the earth surface. So that is called horizontal one. There is also one that is horizontal. So in that horizontal way, there is a formation of magnetic field. Okay. If you combine these two, so this is totally vertical one, electric field. So this is the magnetic field. This indicates electric field. This indicates the magnetic field. This indicates the path of the light direction. So that's why these are called electromagnetic radiations. Here important one, there is a many types of electromagnetic radiations are present. There is many type of electromagnetic radiations are present, which differ in their some of their properties. But the very important thing is this electromagnetic radiation. All type of electromagnetic radiations can be traveled even with vacuum. For example, the wave type of nature can be applied for sound or can be applied for water. So if you compare the water and the sound waves, they travel only in the presence of medium. If there is no medium, so they not at all travel from one place to another place. But the electromagnetic radiations are totally different from them. The similarity, just waveform is similar, but they can travel even in vacuum. Vacuum means there is nothing is there, but even the air is not present. It's called vacuum. Even in the vacuum also they are able to move. Means all types of electromagnetic radiations travel even in vacuum, with medium, without medium, whatever it is. Next, the other one, all electromagnetic radiations are different in their some other properties, but they all move in same velocity, which is equal to speed of light. So all moves with the same speed. They differ in some other characters, but they just move in the same speed. The speed is equal to speed of light. Already we know that the speed of light is 3 into 10 power 10 meters per second, or 3 into 10 power 8 meters per second, 10 meters per second. Okay, so this is just about the nature of light and electromagnetic radiations. Now we see that properties of some. Now we see the sum of the properties of electromagnetic radiation. So properties of electromagnetic radiations. So the main one, wavelength, which is indicated with lambda. Okay, indicated with lambda. So what is the wavelength? So we know that wave is like this always. So the highest part are known as crest. The lower part are known as trough. Means in a wave there is a formation of crest trough alternate takes place. So the distance between two continuous crests, that is two successive crests, or the distance between the two continuous, that is two successive troughs, the distance between the two successive crests, or the distance between the two continuous troughs is called lambda. So numerically its value is also equal to the 2 points. The 2 points length also is equal to wavelength, but a perfect definition we give the successive distance, the distance between the successive crests and troughs is treated as wavelength. So it is nothing but general length is a very small length. So if you take the units, very small length units, that's why we prefer centimeters, millimeters, angstroms, picometers, nanometers, etc. So we see some relations in it. 1 angstrom equal, we know that 10 power 8 centimeters, 10 power minus 10 meters we can say, 1 nanometer equal nano, 10 power minus 9 meters, or 1 picometer equal pico means 10 power minus 12 meters. So these relations are useful in the problem related this wavelength. See the next property. Frequency. So it is indicated with nu. That is named as nu, nu. Okay. So what is frequency? The frequency means the number of waves. The number of waves passed through a particular given point in 1 second time. It is important one. The number of waves passed through a particular point. For example, just there is a wave is moving like this. Just we are referring this point. Just we are observing just a single point. At that point, the number of waves means this total is considered of one wave. Okay, the number of waves moved that point in 1 second of time is called its frequency. Means they are moving with very speed. So it also depends on their length. At a particular point, the number of waves are moving in 1 second is treated as its frequency. Okay, frequency generally, if you take the units are similar units. Cycles per second. Cycles means the one wave is completed as a cycle. Cycles per second. The number of waves moved in a particular point by 1 second, in 1 second. It is also known as heads. Heads are kilohertz. Kilohertz means 10 power 3 hertz. Are nothing but megahertz, 10 power 6 hertz. So here the relation important. There is no need to change the cycles to hertz and hertz to cycle. So because one cycle per second is exactly equal to hertz. Means the problems of calculation of the frequency, the cycles per second directly we can write heads, or heads directly we can write as cycles per second. So just change when there is a kilohertz, megahertz is given. So otherwise cycles per second and the hertz are exactly 100% equal numerically. Then the terminal is only different and the system is only different. So wave number, then we know the new, it's having new bar extra, a bar is extra. It's called new bar. Okay. So wave number means the number of waves present in the frequency we define as the number of waves passed. Here the number of waves present in an unit length. And in a particular length how many number of waves are present, that will be treated as its wave number of that wave. For example, this is a wave. Just we are taking for example 1 centimeter. So there is a presence of 2 waves. I mean they are not like this in the form of in this much bigger one. They are in the very smaller one. So in 1 centimeter there is a presence of many waves are present. Means the number of waves present in 1 unit length. So it may be centimeter or meter. So normally units are treated as per centimeter per meter. Okay. So this is a wave number. Okay. Next. Next, amplitude. So in the term it is there itself, this amplitude means nothing but the size. So it tells about the size. So it tells about the size of the wave means the height of crest. Or the depth. Depth of a trough. Depth of the trough, height of the crest is treated as amplitude. Okay. So these are the main properties about the wave nature, nothing but electromagnetic radiations. So based on these characters, for example, already we discussed about the speed. The speed of all electromagnetic radiations are equal to the speed of light. And all types of electromagnetic radiations can move even in vacuum. But the difference is why there is the many type of many type of electromagnetic radiations. So because, for example, what are the different types? Visible regions, visible light, infrared, ultraviolet, radio waves, microwaves, X-rays, gamma rays. So different are there. So why they are different in them? Due to their difference in their lambda value, nothing but wavelength. Their difference in frequency, nothing but their difference in wave number. So in this some characters, in this some property, they are different. That's why there is a presence of many types of electromagnetic radiations. Okay, we see them later. Okay,